Okay, so this is worksheet 2, number 6, and then whatever else we ask and want to work through together. Function f is defined by f of x equals sine of x plus cosine x from 0 to 2 pi. At what value of x does the graph change from concave down to concave up? So how am I going to know if a graph is concave down versus concave up? So many people not here today. So Jessica, how do I know if a function is concave down? What would tell me that a graph is concave down? And not just like the picture, but which derivative? First derivative tells me increasing and decreasing. Hold on, I need to say the sign of the first derivative tells me if f is increasing or decreasing. And the sign of the second derivative tells me if f is concave up or down. Okay, so which one's concave down? Second derivative. And what would second derivative need to be for f to be concave down? Positive or negative? Negative. So this graph, or this question, is asking where does f prime change from negative to positive? F double prime. So I need two derivatives, and then we'll do the number line thing from there. So first derivative, I need the derivative of sine, and then the derivative of cosine. So Sophie, what's the derivative of sine? Cosine. And Bailey, what's the derivative of cosine? Negative sine. Good. All right, but that's the first derivative. That would tell me increasing and decreasing things. I could find maximums and minimums from that. But I want concavity, so I need the second derivative. So now, Alina, I need the derivative of cosine.
Negative sine.
Negative sine. And Marie, the derivative of negative sine.
So minus.
Yeah, thank you. So minus cosine of x. Okay, got the second derivative. That tells me concavity. I want to know where it changes from negative to positive. So let's first set it equal to 0 and figure that out. And then we'll do the number line thing. So let's see. I'm going to just move the cosine over. You could move the positive negative thing over as well. So I want sine and cosine to be equal but have different signs. So I'm thinking unit circle here. Let's start with quadrants first. Cycle out all the people who are absent. Leah, what quadrants do sine and cosine have different signs in?
2 and 4.
Good. So I'm looking in 2 and 4. First and third are out. Destiny, where in any quadrant do sine and cosine have the same value? Good. That's exactly what I was trying to ask. The over 4s. So 3 pi over 4 and 7 pi over 4. That's where the second derivative is 0. Those might be inflection points. But I don't really know that until I do the sign chart thing, the number line. So I need something less than 3 pi over 4. I probably still want to be on the interval, though. I don't want to go crazy here. So let's go 0 and pi and 2 pi. But I've got options now. Do I want to test those into the second derivative, or the first derivative, or the original? Where do I want to plug those things into? If I want to learn things about concavity. The second. So I need the second derivative at 0, and the second derivative at pi, and the second derivative at 2 pi. And if it matters, I don't really care about the value, I only care about the positives and negatives. So let's see, f of 0. Sine of 0 is 0. Cosine of 0 is 1. So this would be negative 1, which would tell me that f is concave down. If f double prime is negative, f is concave down. I'm pretty sure the alternating thing is going to work, but just to check, I'm going to do one more for sure, and then I'll just alternate if my pattern is holding here. If I plug in sine of 0, or sine of pi, plug in pi. Sine of pi is 0. Cosine of pi is negative 1. So negative 1 gives me a positive answer, which means I'm concave up. And, I can check the last one because 0 and 2 pi should be the same thing. So that one would be concave down. And that does indeed fit the alternating thing. Now let's be careful to answer the right question here. When does the graph of f change from concave down to concave up? From down to up happens right there at 3 pi over 4. Goodness, that was a 6-minute problem there. Second derivative tells us concavity, so I get to my second derivative, set it equal to 0, put it on the number line, and then I can find my concavity intervals and then answer whatever question it asks. All right, what else would you like to see? Did you try number 4? Let's do number 4, and then we'll do number 13. Number 4. Let f be that function. Polynomial, so derivatives will be easy. On which of the following intervals is the graph of f both decreasing and concave up? So decreasing. Macy, how do I know if a graph is decreasing? What would tell me?
Just like going down or it's negative.
Okay, what's negative?
The slope.
The slope is negative. Put that in terms of a first or a second derivative.
Like concave down. Is that what you're asking?
Be careful, concave down does not necessarily mean decreasing. There's concave down. Sometime increasing, sometime decreasing. Back up, what you said about slope being negative is good. What's another word for slope in calculus class? First derivative. So I want f prime to be negative. If f prime is negative, that would mean the slope is negative. That means the function is decreasing. Owen, what would tell me if the function is concave up? F double prime is positive. Okay, so this is kind of an annoying question. It's why I picked to do it. Because I have to do two things. I've got to figure out where it's increasing, decreasing, and where it's concave up, concave down, and then find this overlap thing. So I'm going to have to do first derivative stuff and second derivative stuff. Let's just get through lots of popsicle sticks today. Although, I don't need to go point by point. We can just ask Callie for the entire first derivative of this thing.
6x squared minus 6x times 1.
Good. And I know I need to set that equal to 0, put it on the number line, but while we're doing derivatives, Andrew, what's the second derivative of that?
12x minus 6.
12x minus 6. Okay. So I got to do the same process for both of these. Set them equal to 0, put them on the number line, test the intervals, and then make sure I answer the question correctly here. So the first derivative, take out the 6. That makes factoring kind of easy. So x equals 2 and x equals negative 1. And I'm trying to plan this so I can do these number lines where they're like right on top of each other so I can visually see the overlap better. So let's put my first derivative here. This will be my first derivative number line. Ooh, I almost did something that students do. I almost put 0 over here on the left, which would be a terrible mistake. 0 is in between negative 1 and 2, so I'm going to put 0 there. This one feels pretty straightforward in terms of there's no double roots, there's no crazy derivatives, so I'm pretty sure I'm just going to alternate, especially in the interest of time and space here. So f prime of 0, I can plug it into that f prime or the factored f prime, either way, but I'm going to get negative. So f is decreasing there on that integral. If I wanted to check 3, it'd be easy enough to see that it's positive. The first derivative is positive, which means f is increasing. And I'm just going to alternate for that last interval. Okay, so I'm looking for where f is decreasing and concave up. So I've got my decreasing part, but it has to also be concave up. So now I need to do that same stuff for the second derivative. So set the second derivative equal to 0. X is 1/2. Another number line. I'm going to line it up like with the first number line so that I can just visually see where both things are true. I'm going to check 0 again, but this time I'm checking 0 into the second derivative because I want to know about concavity. 0 minus 6 is negative, so concave down there. I could plug in 1, or I could just alternate. Either way, I'm going to get f prime positive, which means concave up. So concave up, starting at 1/2 and going forever that way. So what I'm looking for is where both things are true. Running out of highlighter colors. Both things are true from starting at 1/2 and going to 2. Both things are true from 1/2 to 2. What a problem. That involves all the things. First derivative tells you increasing, decreasing. Second derivative tells you concave up, concave down. And then just answer the right question.
Can't you just solve this one with just the first derivative? Because the choice is the only one that matches is D.
So, okay, so you're saying like once I looked at that, well, negative 1 to 2 is decreasing.
Oh yeah.
So after I did the first derivative, I think I'd have it narrowed down to C and D. Or B. Yeah. You're right to look for it. It wouldn't help this time. All right, let's switch our brain. Instead of equations, let's do a table problem here. Number 13. This is, I don't want to say it's easier. We're switching like what part of our brain is working here because I'm not taking derivatives. I'm not computing anything. I'm just looking at what they give me. Given the twice differentiable function and then some values, which of the following must be true? Okay. Given the amount of information there, I don't think I want to like start with the table and start making conclusions. I think I want to start with my answers and then see which ones are true or not. So x equals -3, x equals -3. It might be a maximum, and if so, how do we know? But let's look at -3. So x equals -3. The function's at 2. That didn't tell me a whole lot. The first derivative is 0. Ethan, if the first derivative is 0 at -3, what do I know about the graph at -3? If the first derivative is 0, what's that telling me?
If the first row is that's the first derivative is 0.
So,
Can you explain a little bit?
so I know that at -3 the first derivative is 0. So if I'm thinking about what would that mean for the graph, what would that look like if the first derivative is 0? Do you know? What's another word for derivative? Kyler's trying to whisper it back there. Or Luca, somebody. Slope. So the slope is 0. The slope of the tangent line is 0. So I don't know what the graph looks like, but I do know that there's a tangent line of 0. And if we sort of put that together with the second derivative is 2, right? The second derivative being 2, that doesn't really tell me a whole lot, but the second derivative being positive, Danny, what does that mean for the graph? You drew it right. Yes, concave up, which means you'd have got the question right if you drew it correctly. If the second derivative is 2, we're concave up. So, Warren, if I combine the idea of concave up and a flat spot on the graph, what's going on the graph if we're concave up and the first derivative is 0?
A relative minimum.
That's a relative minimum. Which is not what A and B say, so A and B are out. Because that's a relative minimum there. Not really even worried about first derivative test and second derivative test. Do you know which test we used to determine it was a minimum? The second derivative test, because that's how we knew. We didn't know increasing, decreasing on either side. That would tell me that would be a first derivative test. Well, no, I think it's going to have to be D. Let's make sure though. At at 4, similar process here. The slope is 0. The concavity is negative. So that's a maximum. And we found that out by looking at the second derivative. So the second derivative test, there's a maximum at 4 by the second derivative test. Okay, that was lots of good reminders about what the first derivative tells us, what the second derivative tells us.